regular compounding formula and you have PERC. PERC is when you're compounding continuously. When you compound annually, biannually, monthly, daily, we're going to use this one. And N is how many times a year you compound. That's not the time. Time is different. Time is over here. How long? Usually it's over years. Usually it's how much have you accumulated each year, or over 5 years, or over 10 years. The PERC, just make sure that you put the E in there, and that this exponent only goes to this guy right there. All right, so we take a look at these. You invested $2,000 at 6%. Remember to keep it a decimal. N is 4. You're compounding quarterly. I didn't write them all out. I just kind of cut to the formula. And over 4 years. So you plug that in, and remember, money round to the 2 decimal positions. Good? You guys tell me if there's any questions. Okay. We invested $2,300 at 4%. We compounded monthly for 3 years. And we can see what we come up with. We had $6,000 at a rate of 5%, compounded twice a year, semi-annually. Biannually, semi-annually are the same too, for 4 years. And again, leave it in money, two decimals. You invested a lot more this time, $12,500 at 4%, and you only compound annually once for 3.5 years, and that's how much you make. Number 10 is to compound continuously, so that's PERC. It's easier if you use the E over the ln, so it kind of brings you up to the exponent. At 7% for the time, 6 years. And that's where you make your most, compounding continuously. It's very close to the daily, which is the 365. It's pretty close to the daily. Number 11, you didn't have to do. But all you had to do was just substitute in a T. It didn't apply to these. I meant to take it out and I forgot to take it out. It just was a substitution thing. Just substitute it in. Okay. And then 100, substitute in the 100. Good? Okay. Couple of application problems. I wrote up a couple of application problems.
Okay, go ahead, man. Go ahead.
Most of your application problems work off of y equals ab to the x, where a is your initial value. You don't have the sheet, so if you want to just work them out with me or write them down, it's only like 2 words, and then I'll throw in a third half-life one. A is your initial value. B is your rate. Now, the rate says if we double, what is the rate? 2. If we triple, 3. If we half-life, 1/2. Okay? So that's where the rate comes from. It may change when we do a decrease or increase by a certain percent. And then the rate becomes a 1 plus R or a 1 minus R. We never compound anything. The only time you compound is your interest. The rest of it works pretty simply. Just plug it straight through. Okay, so we have a scientist who starts out with 150 units, and again, we're going to graph these to solve them, because we don't know logs yet. We haven't introduced logs, so we're going to do these graphically. A scientist has 150 units of bacteria, I wasn't really sure what to call them, which triples every 6 hours. We want to know, when will the bacteria reach 150,000 units? Now, a nice way for you to start, before you even do that, is to start like this. At the 0, you start with 150 units. At what hour will I triple? 6. I will 3 times this. At another 6, I will 3 times this. I will triple. So this is a nice way to start, so that when you put your formula in your y equals, if your table doesn't look like this, you put it in wrong. Maybe you forgot your cycle. That's what usually happens. So we're going to start with y equals ab to the x. How much do we initially have? 150. And we are tripling, so my rate is 3. And my time is in hours right now. Time in hours. Am I tripling every hour? No. And I can see from my chart, I'm tripling every 6. So how do I write my cycle? Every 6. Divide by 6. Every 6. So don't I want 12 divided by 2, 6 divided by 6? 12 divided by 6, 6 divided by 6. Every 6 hours I want. This is my cycle. So what my point is for doing this, if you just put raised to the x, you're going to see it at 1, at 2, at 3, and you're going to say, wait a minute, it's supposed to be every 6. That tells you your cycle was off. Now, this is what I want to end up with. I want to know, when do I reach 150,000? So because our exponent contains the variable, we're going to graph these. We can bring it down when we do logs next week, but today we're just graphing. All of your applications take place in quadrant 1. All of your increasings look like this. All of your decreasings look like this. The increasing, they start out slowly, and then they grow faster and faster because your numbers are getting bigger and bigger, that you're doubling, tripling, whatever you're doing. Your decrease starts out quicker because you start with a bigger number and you half it or you reduce it by something, and then it trickles off. And we're going to intersect on all of these. We're going to do intersects. So we've got a situation like this, and it doesn't start at the 0 because we've got to start with some bacteria here. So we put it in your calculator, and maybe the tricky part here is changing your windows. So we've got to work on your windows. So we say 150 times 3 raised, and if you have the 83s or that doesn't have the software, you have to put parentheses around this. X divided by 6. Okay, I want to know when it reaches 150,000. I have to adjust my windows. Now think of this logically. You're in quadrant 1, so your mins are zeros. My max, well, I know my max. I want to know when it reaches 150,000. So that'll put my line right at the tippy top. So maybe I'll just do 160,000. Okay. The part I don't know is my years, or my hours, my times, my days, my minutes, whatever my time has to be. So start at 20 and see what happens. Now, when you graph this, and you can see your graph coming way over here, you know it's not a straight line, it's got to be curved, right? And then my things are not meeting. What do I have to change? Your X max, and probably a good chunk of it, right? So maybe instead of doubling, I'll go to 60. I got a ways to go there. Now you see the steepness of your curve a little better? You see the curve taking off? Well, if you ever get a straight line, always make sure you have your exponent there, because sometimes you forget to raise it up there. Make sure you can see them cross, and then do an intersect. Number 5, enter, enter, enter. And give me 3 decimals. So in 37.726 hours, I will reach 150,000. It's pretty fast. That bacteria is growing pretty fast. Good. Make sure you give me 3 decimal points on your time. Questions? Very simple. AB to the X. Okay? You guys try the next one. I'll erase this and you try the next one. I don't think I can move this up. So Can you read it down there? We got a population that's decreasing. It's not cutting in half, but it's decreasing. Set up a formula for it, and let's check the formula. Start with this. What's your A? What's your initial value? 100,000. It's a lonely town. It's going to be decreasing its population. How do I show that rate of a decrease of 15%? Good. 1 minus R. That's your rate. So 1 minus 0.15. Good. And then my time. My time is what? Every year. Every year. Not every 6 years, not every 5 years, every year. Now, I want to know when it reaches half of what it was now. Good. Y will equal 50,000.
Can you just make it 1 and 2?
Yep, this is your Y1. This is your Y2.
Like you make the actual values themselves.
No, because you got to know exactly when. You're not cutting it in half all the time.
Okay.
Yeah. Wait, I wonder. Maybe you can. Because we double, we triple, we do the same way with the half. I don't know if it'll work over 1%. So try the graphic for me. Yeah, you can.
Yeah? Okay.
Okay, and again, if you start out logically, at the 0, you start out with 100,000. At the next year, you've decreased 15% of it. Okay, then off of the next year, decrease another 15%. Off of the 85,000. So, if your graph is not looking like that, then something's off. So what did you find out for X? 4.265?
Yep.
65, thank you. Now Robert had a thought here. The same way we did with the triple, the 1 to 3, the double 1 to 2, you could half this 2 to 1, but the opposite way. Like we did before the half, we did the triple and the double, we did a 1 and a 3. This one's a half, so you'll have to be a 2 to a 1. If you wanted to do it that way. You're probably better off keeping your 100,000, your 50,000. You just have to adjust your table. Can everybody graph this or no? Yes. Uh-huh. Your X is your years. Your Y is your amount. It's there, you just can't see it because you made it different. Yeah. Good? Okay, let's do a half-life. Okay, a scientist starts out with 35 units, or 35 grams of a radioactive element. That has a half-life of 15 years. I want to know when will it reach 3 grams. So he starts out with a radioactive element, 35 grams of this element, that has a half-life of 15 years. Every 15 years, it cuts in half. I want to know when will it reach 3 grams. Start out with your equation. Always start like this. What's your rate this time? What do I want to do? Half. I want to cut it in half. And I want to do it every year. Do I want to cut it in half every year?
15.
Every 15 years. There's my cycle. How much did I start with? And when do I want to reach? 3 grams. So there's your Y1, and there's your Y2. Adjust your windows, because we were at a pretty big scale before this. It works out much better when I move my calculator over here, not in the middle. So what should I set my windows at? 35 maximum for X? For Y? 35 maximum, yeah, make it 40. It's decreasing. What should my X max be? My X max is my years. It's decreasing every 15 years. Okay, let's make it 100, see what it looks like. So there's my element decreasing. And there's my intercept. Number 5. It's 53.165 years. Now, in my table, I should see, when I start at the 0, I should see 35 grams. When I get to 15, I should see what? 17 and a half, right? It should, after 15 years, I should be at 17.5. See it? Now if I forgot my cycle, and I just decreased, watch what happens. If I forget my cycle in this, and I just went by X, and I forgot to say divide by 15, when I do this, watch my table. Oops, I'm still working. Look what my table looks like. It's decreasing every year. Whoa, but I said every 15. So that's why I know I'm wrong. So if you think this out logically, you say, what's the first year that it'll decrease to half? That you should be able to find that on your table. If you can't, then redo it because it didn't work. Okay? So this is what you should expect to